gain at the uh, gain at the gate threshold voltage. One of the commonly used figures of merit for an inverter is the small signal gain of the inverter when it is at the operating point. Vn equal to V out is equals to Vt H. To find this gain, the transistors should be replaced by their small signal models described in chapter 3. The small signal model of a MOS transistor at low frequencies where the capacitances have been removed. It is shown in figure. This model was described in chapter 3, but for convenience the equations for the various parameters will be repeated here. Here you can see the figure, the small signal model of a MOS transistor at low frequencies. The voltage controlled current GM-VGS is responsible for the transistor operation. In an ideal transistor, this will be the only component in the model. The transconductance GM is given by GM equal to nu n C naught x W by L VGS minus VTN is equals to nu n C naught x W by L V EFF equal to root over 2 nu n C naught x W by L ID. The second voltage controlled current source VGS GSVS models of the body effect it is responsible for the decrease in current as the source voltage Vs increases. This is the reason its direction is opposite that of GM-VGS. In many introductory tests, this current source is not included in MOS small signal models. For the pseudo and MOS inverter, the sources of both the drive transistor and the P-channel load transistor are connected to the ground and VDD respectively, which are both small signal grounds. Therefore, both transistor Vs is equal to 0 and the current source modeling the body effect can be ignored. The parameter of the model is the output resistance of the transistor RDS. For transistors that do not have short channel effects, this models the reduction of the channel length due to the increase in the length of the pitch off region at the drain end of the channel, which when the drain voltage increases. For this case, it is approximately given by RDS is similar to L alpha root over VDS plus VT by ID, where alpha is the process dependent constant on the order of 5 root over V by nu m. That is L in micrometers. For transistors having short channel effects, the output resistance will be much smaller. For this case, we have RDS similar to 1 by lambda ID, where lambda must be where lambda must now be empirical derived from transistor measurement. This must be done for every different channel length that is to be used in deriving the small signal model for the inverter. VDD is replaced by ground as it is assumed to be a constant voltage. This leads to the small signal F equivalent circuit shown in figure. Note that Vg minus 2 is equal to Vs minus 2 is equals to 0 implies both the current sources Gm minus 2, Vgs minus 2 and Vgs minus 2 both the current sources Gm minus 2, Vgs minus 2 and Gs minus 2, Vgs V and V Gs minus 2 Vs minus 2 are 0. Also, since Vs minus 1 equals 0, Vgs minus 1 Gs also since Vs minus 1 equal to 0, Gs minus 1 Vs minus 1 is equal to 0 as well. This allows the circuit to be simplified to that shown in figure B. The gain shown readily calculated be V out by Vn equal to minus Gm minus 1 by 1 by R ds minus 1 plus 1 by R ds minus 2. In the MOS models used in SPICE, lambda is specified by the lambda parameter. If this is specified, the output impedance is calculated using equation independent of the transistor cell. Thus, a different lambda and therefore model statement should be used for every different transistor length used. Here you can see the figure, a small signal equivalent circuit of pseudo NMOS inverter, and B simplified small signal equivalent circuit of the inverter. This gives a gain at the gate threshold voltage on the order of minus 15 to minus 50 depending on processing parameters of a particular technology. Thank you.